With all those introductions, we want to welcome you. Thank you for making an effort to come. And Del and I had talked about this. We were going to make this kind of a training session for Agro K staff and put them in good stead in terms of this technology, how to use sap analysis in terms of evaluating crops. But then the more we talked about it, we said, well, we have some growers that we have gone to their farms and done sap analysis for them and with them. That they've been participants in using this technology, and maybe they should be invited too to just pass this on. And then there were some other key people. We just felt this would be a real benefit for them to come and participate in this. So I want to just introduce you to how I became aware of sap analysis. About 3 years ago, I got a call from a grower in Pennsylvania who had a greenhouse operation, and they had a lot of blossom end rot. They saw an ad that we had run on blossom end rot, calcium for blossom end rot. They called and said, could you help us? We seem to have a serious problem, and what can be done? And so we start with the soil and any plant tissue analysis, but the problem was that they'd put down manure in their greenhouse, and they had so much organic N coming up, we couldn't manage it, and they just had a horrendous problem with blossom end rot. So basically, they had to clear all that out and start all over. But in working with them and helping them grow greenhouse tomatoes, we would fax back and forth tissue tests, soil tests, and one day they sent me this sap analysis, which I had never heard of, and they said, well, this is a test we just had done. You measure old leaves and new leaves and you compare them, and this was the results on a test we just ran in our greenhouse. What do you think? So I'm looking at it, and I really don't know what to think. They have some good and bad and excellent, and so I said, well, what do you think we should do? Well, based on this, I think we need to put more magnesium on, or we need to spray more calcium. And so that was kind of I started working with them over a 2-year period, and we were dripping a lot of nutrients through their irrigation as well as foliar feeding. And they were really all about quality. They grew a lot of high quality tomatoes and sold them at a auction, and people from New York drove all the way to Pennsylvania to buy these tomatoes. So it was quality that really sold them. So I was talking with Del about it. I showed him, and he said, well, yeah, I've heard a little bit about that. And the more we talked, we said, well, let's look into this more. So eventually Eric went to a sap testing seminar out in Ohio, and then Rob Ford went to one in Pittsburgh. So we see this technology as a tool to understand what is happening in the plants. Agro K we're always in the process of developing and trying to utilize new technology in growing crops and being more effective at making quality. And so we found this technology, and that's why we invited John Kemp to come today, is to explain it so that you understand what we're trying to do in terms of our products. We're trying to understand how that plant is responding from the soil as well as foliar applications, and how we can better help growers manage the nutritional needs that they have. So with that introduction of how we got into sap testing, or sap analysis as we call it, John Kemp, I'm going to let you introduce yourself, John, to give a little background so they kind of know where you're coming from. But welcome. Look forward to spending this morning hearing from you.
Well, good morning, friends. Happy to see all of you this morning. There are, so thank you, Larry, for that introduction. For those of you who were not here yesterday, the genesis of my experience with sap analysis really begins when I did a lot of research in plant physiology and trying to understand how some plants could be resistant to disease and insect pests while others were susceptible. And I learned that plants have an immune system that can be supported, and when that immune system is supported with the correct nutrition, plants have the potential to be resistant to disease and insect pests. And there was a lot of research which indicated that there were specific nutritional correlations to certain diseases, but we were not able to identify those correlations using tissue analysis, which was a major frustration that I had with tissue analysis. So a number of years ago, 5 years ago actually, we started working with sap analysis, tested it, kind of looked at it on a very small scale for a couple of years. And then for the last 3 years, we have been using sap analysis on a very intense scale, a lot of different crops all across North America. And so the discussion today, Del and Larry asked me to really talk about how to use sap analysis from a really practical perspective. How do we use this information to make management decisions in the field? And as I was putting this training together, I asked myself the question, what is the key information, what's the critical information that I would have liked to know 10 years ago when I started doing agronomy work? And what I realized also is that for many of in the ways that we think about nutrient management, the way we make recommendations in the field, there is a lot of knowledge, there's a lot of information about each of these different elements. There's a tremendous amount of information about calcium, a lot of information about manganese, a lot of information about zinc. But the reality from a practical management perspective, we tend to focus on very few singular elements or a singular pieces for each element. We manage each element to accomplish a specific purpose, and when we manage that element well, then everything else tends to fall into place all on its own. So for the sake of the discussion today, the discussion today is kind of framed into 5 major discussion areas that we'll be talking about. The first piece is I wanted to kind of give you an overview of the major physiological processes that impact nutrient movement and nutrient flow within plants so that you can understand nutrient mobility and how nutrients are moving around. That's going to be the first piece that we talk about. Then after that, we're going to focus on each of the individual minerals, and I'll describe for you, the purpose of the discussion is I want to try to build an image for you in your mind. What is the one thing that you need to know about each of these elements? What's the one thing you need to know about calcium? What's the one thing you need to know about boron? And then the third piece is that I'll be discussing will be an outline of the critical nutrient interactions. So there are dozens of different nutrient interactions, hundreds in fact. But in terms of actual practical management, we find that there are 7 or 8 of them that we need to manage consistently, that show up consistently. Those are the ones that you really need to pay attention to and really need to be concerned about. All the remaining 155 or whatever the number is are for people who are studying them academically and are really concerned about fine-tuning it. From a practical management perspective, we don't need to know all that extensive detail. And then the last piece of the discussion is, okay, we've identified all the parts. Hopefully we've identified all the different puzzle pieces. Now, how does the puzzle actually go together? How do we make it practical? How do we turn this into practical recommendations? And I'll describe the process that we use to make recommendations, how we use this information, and what recommendations look like. And then from that, hopefully our goal is to have all of this discussion, kind of this outline, wrapped up by about 2 o'clock this afternoon. And then from 2 to 4 this afternoon, we're going to go through an exercise where we will look at a series of SAP analysis, and we will go through the process collectively as a group of making recommendations based on those SAP analysis results. The goal for the day is I want you to be able to, at the end of the day today, walk out of this room with a very solid foundation, a very solid understanding of how to read a SAP analysis report and how to make recommendations from that, and being at least to some degree comfortable with that test and understanding what is being reported. So, we started using SAP analysis in our consulting work at Advancing Eco-Agriculture in 2011. And from that initial work, we founded an independent company called Crop Health Labs in 2014. Crop Health Labs is based in Ohio, is currently running as a virtual laboratory until we develop our own laboratory here in the US. At the moment, samples are still being analyzed in the Netherlands. And what that process looks like is that we are amalgamating or bringing together all the samples in Ohio and packaging them, refrigerated, and overnight airing them to the Netherlands, where they're all analyzed, and the results come back by email. At the moment, depending on which region of the country farmers are in, we're having anywhere from a 5-day to an 8-day turnaround on results. From the day the sample is collected, the farmer's out in the field collecting the samples, the results are back. He has the results back sometimes in as little as 5 days, and at the outside, 8 days. And we're looking at constantly condensing that. But that's, we feel, a very good turnaround. It's very competitive, even with a lot of laboratories here in the US. So, a lot of the information, because of the, a lot of the information today is going to be a very high-level overview. It's just the core practical information that I think every good farm manager and every agronomist needs to know. If you want to have a much more in-depth review, there are 3 books that I highly recommend. These 3 books are kind of the core reference material that I use for almost all the research that I do to follow up on. This first one is Mineral Nutrition of Higher Plants. This is the 3rd edition. It was edited by Petra Marshner. The second is Mineral Nutrition and Plant Disease. This book identifies many of the correlations between specific disease pathogens and specific nutrient imbalances. And the third is the Plant Analysis Handbook. These 3 books in combination are kind of the library, if you will, where a tremendous amount of research has been amalgamated and put together into a very concise, very clear format. I reference these books almost more frequently than I do almost all the other books in my library combined. So, let's talk a little bit about plant physiology and how nutrients move in plants. Within plant structure, there are 2 different types of nutrient transport tissue in plant structure. The first is the xylem, or the phloem transport. So phloem transport moves sugars and sugar water from the leaves, from the photosynthesis process, to the various sugar sinks. There are 3 different sugar sinks. The first and the largest sugar sink within the plant usually is the root system. Most plants over the course of their entire lifetime will transmit as much as 50 to 70% of their total sugar production down through the roots and out through the roots as root exudates. It's a tremendous amount of sugars that are moving to the root system. The second major sugar sink is the new growth at the top of the plant, where that sugar is being used as an energy source to drive and fuel growth. And the third major sugar sink is the fruit. Now, the fruit is very different from the other 2 in that the fruit are a storage organ. So potassium is the locomotive that drives carbohydrate translocation, sugar transport within the system. So what happens, this is one of the reasons why many berry crops, fruit crops, tree fruit, any crop that stores a lot of sugars and a lot of carbohydrates in the fruit has very high requirements for potassium, because there is in essence a one-way entry gate for carbohydrates and consequently for potassium into the fruit. For the sake of this discussion, the interesting part about phloem is phloem transport is sugar water. The solution that the phloem is moving is 16% solids, 16% dry matter. So we're talking about something that has a very high sugar content. And the interesting part about the phloem is that it does not transport calcium and it does not transport manganese. So this means that when you apply a foliar spray of manganese onto the leaf surface, that manganese is not going to be transported into the fruit. The same holds true of calcium. When you spray a foliar application of calcium on a leaf surface, that calcium is not going to be transferred into the fruit unless that calcium or manganese is in the chelated form. This is why foliar applications of calcium chloride, calcium acetate, and so forth on Honeycrisp apples have a very limited effect in moving calcium into the fruit because they're dependent on the calcium that actually lands on the fruit itself rather than on the leaf. Since the calcium chloride that lands on the leaf surface is not in the chelated form, it's going to stay in the leaf. It's never going to be transported from the leaf into the fruit. So the second type of transport tissue is xylem. And the xylem moves water from the root system up throughout the rest of the plant. So the water movement from the root system up throughout the entire plant, this is a very watery solution. It's 98% water, has a very slight nutrient concentrations. So this xylem transport is the only real source that the plant has of calcium and manganese. So what this means is calcium and manganese, this is particularly important for very high fruit quality and for very vigorous and disease-resistant new growth. This means that we need a constant supply of calcium and manganese each and every day. If we're growing a crop and one day the soil is no longer capable of supplying that crop's demands for calcium or manganese, on that day the calcium and manganese levels will drop in the new growth. And now that new growth has an increased susceptibility to diseases, and also you have less calcium and manganese moving into the fruit. So one of the important pieces to discuss here is also to discuss how water moves in plants and the differences between photosynthesis and photorespiration. So you guys know what I'm talking about when I talk about photosynthesis versus respiration? I'm talking Greek completely, okay? Some of you get it. So photosynthesis is the process, this is how a plant will utilize water in ideal growing conditions. So in ideal growing conditions, it's a warm, pleasant day at 75 degrees. The majority of the water flow is being used for photosynthesis. And photosynthesis is happening the most rapidly in newer leaves, and there is also water being used in the new leaves to drive growth. So this means when you have this 75-degree day, and I'm just making up the numbers here for the sake of an example, let's just say that on this ideal growing day, 65 to 70% of the total water that is absorbed from the root system goes upwards to the new growth. And only about 30 to 35% goes to the old leaves for the photosynthesis process. Now, let's switch that around. If we have a 95-degree day or warmer, actually it's about, it varies from crop to crop, but for most of the crops that we're growing, it's above 78 degrees Fahrenheit. Then at that trigger point, these plants start not just photosynthesis, but also photorespiration. And respiration is a plant's cooling mechanism, is the cooling process to protect itself from overheating. So it's basically plant sweating, for lack of a better term. So now, when you have photorespiration, this water movement dynamic completely changes. You now have the majority of the water, because the lower, older leaves are much larger. They have a larger surface area, usually. So now this dynamic changes where you might have 50 to 60 to 65% of the water going out through the older leaves, and the new leaves at the top only get 30 to 35% of the water. What that means is that in those high stress, high heat conditions, calcium and manganese is not moving up to the upper part of the plant. It means calcium and manganese are settling out in the lower, older leaves. And the same also holds true to a certain degree of magnesium. So when you conduct sap analysis throughout the course of the growing season, when you have these high heat conditions, you will often see accumulating high levels of calcium on the lower, older leaves. It's an artificial number. It's a fake number. That calcium isn't actually physiologically active in those lower leaves. It tends to just sit there and be deposited there because that is where the majority of the water is going. So calcium follows water. Calcium follows the water stream. And this is very important because one of the pieces that I'm certain you have observed with the nutrition programs that you're working with, one of the things that we certainly have observed is that when plants have very strong nutritional integrity, they have a much greater degree of climate resilience and weather resilience. So they will continue photosynthesizing at higher temperatures. So when they continue photosynthesizing, they don't switch to respiration nearly as quickly. You can actually buffer this out. You can buffer how water moves to a large degree by proper nutritional management. And you can keep that calcium moving up to the new growth much longer in higher temperature conditions. Actually,
I'm sorry, I don't
yep.
mean to interrupt.
Please interrupt at any time.
Like overhead irrigation for use for cooling, does that, and it, it'll keep the plants cooler like apple trees?
Yep.
Then will the tree continue to
as long as the tree is,
photosynthesis?
yes. As long as the tree is cooler, it will continue to photosynthesize.
Okay.
This is particularly relevant also for whenever we are growing crops in high tunnels. So tomato production in high tunnels, for example, they tend to switch to photorespiration very quickly. And one of the pieces that we'll talk about later is how in the photorespiration process that also triggers the production of ammonium in the plant leaf structure, which can be a substantial health challenge and a health concern for crops. So, yes, really great question. By the way, there's many different pieces to talk about, but I welcome your interaction, your input, and if you don't raise your hand and don't speak up, I'm just going to keep right on going. So, welcome your engagement. So, the next piece that is also really important to understand is to understand that each plant has a 24-hour photoperiod, 24-hour photosynthetic cycle. So, there are three different periods within each 24-hour photosynthetic cycle. The first period, we'll say, is from sunrise to approximately approaching sunset. From sunrise to approaching sunset, where you have very active photosynthesis, you have a spike of photosynthetic activity, and the leaves accumulate very high sugar concentrations in the leaf itself. Then, starting about mid-afternoon, and obviously where mid-afternoon is depends on latitude and also to a degree on the crops you're growing, but let's just say for the sake of discussion about 5 to 7 p.m., the plants start moving and translocating those sugars from the leaves, from the source, to the various sugar sinks. So I talked about the various sugar sinks earlier. You have shoot growth, root growth, and then fruit development and root exudates. You have these three sinks. Actually, two of these go to the root system. So what happens is from 5 to 7 p.m. until about 1 to 2 a.m., all of those sugars should be moved out of the leaves and to the sinks. So this is when the phloem transport, this syrupy liquid within the phloem, is actually moving around very actively within plant structure. Then the third stage is from about 2 to 3 a.m. until dawn, usually around 8 o'clock in the morning. In that time period, the plant is now using all of those sugars that have been transported to either the shoots at the top, the root system, or into the fruit, is now being metabolized and utilized to build cells, to build cell membranes, and is used both as an energy source and as a building block for growth and development. 80% of plant growth, 80% of cell division and cell expansion for most plants happens between 3 o'clock and 8 o'clock in the morning, every 24-hour photoperiod. So there are these three very distinct cycles that happen. And so this is really important because this speaks to the best timing for applications of foliar nutrients. It also speaks to some of the challenges. I'm not aware that any of you historically are using petiole analysis, but this describes very clearly why there is such a huge degree of variability with petiole analysis and why it is not consistent. Because the petiole is the nutrient transport pipeline. And so in that 24-hour photoperiod, you have two distinct stages. You have early in the morning when there's a lot of nutrient and water transport through the xylem. You have a lot of, or not early in the morning, during the day, during the photoperiod, you have a lot of water movement up for photosynthesis through the xylem transport, and then in the evening you have a lot of phloem transport. So there's a lot of nutrient movement happening in the petiole for the majority of the day. The only time period where there's not a lot of nutrient movement is early in the morning. So there was another point that was important. Photosynthesis, nutrient transport. Forget what it was right now. I lost my train of thought. All right, guess that's all. Any other questions? Any questions?
Foliar feeding?
Oh, foliar feeding. Yes, thank you. That was the thought that I had in mind. So, I'm often asked the question, when is the best time to foliar apply nutrients? And there are two correct answers. The first correct answer is that most plants absorb nutrients the most effectively at the highest degree of humidity. So when you have the highest humidity is when they'll absorb nutrients the most effectively, because they remain liquid on the leaf surface for the longest period of time. The second correct answer is that plants absorb nutrients the most readily in this period of very rapid cell division, cell expansion from 3 to 8 a.m. in the morning. Now, yeah, right. You're not going to go out and do foliar feeding at 3 o'clock in the morning, right? So when possible, when appropriate, we suggest farmers that they do foliar feeding very early in the morning, and if that's not possible, then the second best alternative is late evening, because they are then on the leaf surface. Usually there's high enough humidity, they're still on the leaf surface for the early morning absorption. So, great reminder, Larry. Any other questions on foliar applications? You guys got it all figured out. All right, so there is one very key aspect of sap analysis, which is that, and later this afternoon we're going to be looking at some actual reports, but with sap analysis, we measure at two different points on the plant. One is we measure the new growth, the last fully mature leaf, and then we also measure the old growth. In the case of apple trees or tree fruit, it's generally the last or the oldest leaf on the new shoots or the spurs. And so the reason we do that, this is what we call differential testing. We're measuring the differences between old and new and seeing how nutrients are moving around and flowing around inside plants. And so I'll be discussing the mobile elements and how they move around and how we can see when plants have adequate levels of different minerals or are deficient. But the interesting point, the specific point is that plants have certain points in which they will do everything possible to keep the mineral balance exactly where it needs to be. And those points where they desire optimal nutrition during the vegetative stage are the new growth shoots. So when you have plants in the vegetative stage, they will do everything they possibly can to keep those new shoots at the optimal nutritional balance, including sabotaging older growth and absorbing nutrients from older leaves and moving them to the new growth, or vice versa. If they have a surplus of a certain element, such as nitrogen or phosphorus or any of these mobile elements, they will store that surplus in the lower older leaves. This is the reason why many diseases, most diseases, there's a few notable exceptions such as fire blight, but most diseases begin on the older leaves because the plants do everything they can to keep the new growth healthy. So then the second point at which plants do everything they can to maintain optimal nutrient balance is the fruit, during the fruit fill stage. And this is kind of has the potential to be a two-edged blade, because one of the challenges that we have, many growers are doing fruit analysis throughout the growing season to evaluate the integrity of the fruit. And that can sometimes be a misleading indicator because the plant is going to do everything it can to keep that fruit balanced, even at the expense of the rest of the tree. So this is one of the things that we see very pronounced with Honeycrisp apples, for example, where we have a apple that genetically grows to be a very large size because of very large cell size, but it will actually sabotage leaves in order to produce that large fruit. And you end up after harvest with really unhealthy leaves as a result. There is a lot of discussion today about producing nutrient-dense foods and about nutrient density, producing food as medicine. And we need to be really careful how that conversation is defined. and how nutrient density is defined. So there's just this general expectation that blueberries are a nutrient-dense food, or that kale is very nutrient-dense. And we have made a very interesting observation that we believe we need to be very careful how we define nutrient density, and nutrient density cannot and should not be defined in terms of mineral density. There's more to the story than just mineral balance. Here's why. What we've observed is when we have a crop where all the nutrients are balanced in the SAP analysis across the board, everything is at optimal ranges, exactly where we think it needs to be, with the exception of one or two elements. Let's say they're phosphorus and manganese for the sake of discussion. And we put on a foliar application of phosphorus and manganese. We address the specific deficiencies that need to be addressed. In the next 48 to 72 hours, all the nutrients across the board will drop by 30 to 40%. There's this tremendous drop. When you look at the lab report, there's this drop of nutrient concentrations that is profound, and what on earth is going on here? That's what happens when you look at the piece of paper. When you're looking at the crop, what actually happened is when you hit those specific deficiencies that are holding back photosynthesis, there is this tremendous explosion of photosynthesis, and the crop biomass grows tremendously. And I am completely convinced that there is, and in fact we've measured this, there is a change in leaf size that can happen very quickly. We tend to expect that leaves have this once a leaf is fully developed, then it's going to stay that shape and that size for the rest of its life. But we have found that we actually have an expansion of leaf size. So you have this expansion of biomass, and all the nutrients across the board tend to drop in all that biomass as a result. Now, so if you define nutrient density in terms of mineral density, you would say that you have a less mineral dense crop. However, when you look at all the production of the plant's secondary metabolites, the anthocyanins on blueberries, resveratrol, all these phytoalexins, all these immune compounds that plants produce, the concentration of those immune compounds spikes from 8 to 10 times or more. There's a substantial increase in all the immune compounds that gives plants resistance to disease and insects, and also that transfers immunity to people. So, the Mulder chart is a chart that identifies all of the different nutrient interactions, those elements that antagonize, that have antagonistic and synergistic relationships with each other. I gave some of you some homework yesterday. You've memorized this by this morning, right? Yeah, good. Happy to hear that. So there's there's a bewildering array of different nutrient interactions that take place within plant systems. And the developers of SAP analysis developed their own nutrient interactions diagram that is not fully perfect, but it is much easier to understand and is much more clearly describes some of the nutrient interactions that are taking place within plants. And I want to kind of describe some of the things that we have learned with SAP analysis and that are reflected in this diagram. So we put this diagram together to really explain and describe some of the nutrient interactions that we see taking place in plants. If you look at this diagram, it's divided vertically and horizontally. On the left side of the chart, we have all of the cations, the positively charged elements. On the right side of the chart, we have all the anions, the negatively charged elements. At the top of the chart, we have all of the major elements, the macronutrients, calcium, magnesium, potassium, and so forth. And at the bottom of the chart, we have all the trace minerals. When we work with soil analysis, we understand that each different given soil type, depending on how much sand, silt, and clay it contains, has a finite mineral holding capacity. We call that CEC, cation exchange capacity, or anion exchange capacity, which is not often discussed, although it should be. And we have not applied that same crop to plant nutrition. However, each cell within a plant structure has a finite mineral holding capacity. And what the team in the Netherlands observed is that there is a finite mineral holding capacity for cations, and there is a finite mineral holding capacity for all the macronutrient anions. So when one of these elements is in excess, it will actually has the potential to create a deficiency of something else. So if we have excessive levels of ammonium, for example, NH4, then it has the potential to create a deficiency and specifically antagonize one of these other elements. And if we go back to the Mulder chart, if we go back to the Mulder chart, this chart often will identify precisely when you have an excess of one, which of the others is most likely to be reduced. But I can give you a very general example, a very quick example. Right now we see that calcium is often the element that is the first to be excluded. It's the first to be pushed out because it is one of the most difficult for plants to absorb. And there are two elements which in particular have a very strong antagonistic effect to calcium, and those two are ammonium and potassium. Whenever you have high levels of ammonium or ammonium application, it will actively suppress calcium absorption, and the same holds true of potassium. When you have surplus levels of potassium, plants will absorb potassium to the exclusion point of calcium, where they will actually exclude calcium uptake. So, yes?
What's your opinion on what's an excess?
I let the plants tell me that.
Okay.
So, I'll be describing how we define excesses, but in essence, what we're looking at how nutrients are being moved around, and it is worth mentioning that in the case of nitrogen, on the SAP analysis, nitrogen is measured in three different parameters. They measure nitrate nitrogen, ammonium nitrogen, and total nitrogen. Those three are broken out and are separated. And it is our goal, we see consistently that the healthiest plants, the plants that have the greatest degree of disease and insect resistance, have nitrate and ammonium levels none detect. They have zero. And yet they still have very high levels of total nitrogen. The total nitrogen is nitrogen that is in the form of amino acids and proteins that is not in the form of nitrates and ammonium. So,
So, John, just to be clear, ammonical nitrogen, similar antagonistic relationship as potassium to calcium?
Yes, to a lesser degree. Particularly, we see that, so I'm not saying, for example, that if you put on ammonium, nitrogen, the plant is going to stop absorbing calcium. That's not what I'm suggesting. What I'm suggesting is that if you have an ecosystem where you have a specific crop, a specific soil type, that the crop is doing a very poor job of absorbing calcium in the first place, you will just provide an additional detriment by using ammonium nitrogen. You will actually suppress calcium absorption even further. So this idea of antagonistic relationships between different nutrients has been very intriguing because what we have observed is there's this ideology, this paradigm within agriculture that we constantly need to be applying more materials. If we have a zinc deficiency, we need to put more on. If we have a phosphorus deficiency, we need to apply more. If we have a calcium deficiency, we need to apply more. What we have observed is that the majority of nutritional imbalances, particularly for all the macronutrients, all the major elements, phosphorus, chloride, sulfur, nitrate, nitrogen, magnesium, potassium, calcium, many of those, when we have imbalances of those major macronutrients, in 80% of the situations that we observe, those imbalances are actually created by excesses of products that the farmer applied. So in many instances, we actually have been able to have a substantial impact by reducing nutrient applications. I'll give you one example of something that we observed in eastern Pennsylvania, Lancaster County, Pennsylvania, and into Maryland. We work with a distributor in eastern Pennsylvania, Keystone BioAg. They work with several hundred operations, many of which grow tomatoes, both outdoors in the field and in high tunnels. So in this local area, we have limestone-based soils. We have very high calcium content, high calcareous soils, high calcium content, high soil pHs, and they also have more livestock and more livestock manure than they know what to do with. So we have soils that have extremely high levels of calcium, extremely high levels of phosphorus, extremely high levels of potassium from excessive manure application, and the tomato crop and many of the crops are starving for phosphorus and calcium and potassium and magnesium across the board. So when we were using tissue analysis, with our tomato crops, there were two deficiencies that just showed up consistently on many of these different farms. Many of these crops were not doing a good job of absorbing potassium, and they had extremely low levels of manganese. So our solution at that point was to apply either manganese sulfate or a manganese EDTA chelate as a foliar spray. And we would put on a foliar application, we'd see the manganese numbers come up, and we thought that the problem was fixed. When we started using sap analysis revealed a very different picture. We would put on the manganese foliar sprays, and we got no movement on sap analysis. The manganese numbers did not change from manganese sulfate applications as a foliar. There was no response. And so this led us down a very interesting pathway of really looking at the specific oxidation states, what oxidation states trace minerals needed to be in, and the chelation agents that were used. And so we started using completely different forms of manganese where the manganese levels came up very quickly. We got a very strong manganese response. And then something really unexpected happened. As we increased the manganese levels, all of a sudden the potassium levels came up all on their own without applying any additional potassium. Our sales of liquid potassium in eastern Pennsylvania dropped by 90% in 1 year. Just boom. They didn't need it anymore because they fixed the manganese problem. So there was this tremendous response. We actually saved those farmers hundreds of dollars per acre in potassium applications simply by managing manganese. And we were able to see what was happening with sap analysis. The sap analysis shows us whether the nutrients are actually being absorbed into the leaf or not. And tissue analysis also shows us what is still the residue on the leaf surface. So this is, I always kind of had a question mark in my mind about how accurate sap analysis is at not being contaminated with what is actually on the leaf surface. But we have had farmers that are organic farms that are putting on very strong sulfur applications of elemental sulfur for disease control, and their sulfur nut levels on their sap analysis come back deficient. They're very low sulfur levels because that's what's actually low in the plant sap. Yes?
Maybe could you contrast the difference between sap analysis and tissue analysis? Are you going to do that?
Yes, okay. I can do that. And I'm sorry, I missed a question over here, forgot about it. I'll come back to you in just a moment. So with tissue analysis, you collect a single leaf from the last fully mature leaf on the plant, send it to the laboratory. The laboratory gets that, when they get that sample, they dehydrate it, ash it essentially, and then they report the nutrient content of that material on a percentage dry matter basis. What is the percentage of calcium in that total dry matter? Sap analysis is completely different from that in that we're collecting that same leaf that we would for tissue analysis, the last fully mature leaf, and then we're also contrasting it with an old leaf at the bottom of the shoot or at the bottom of the plant. We send those two samples to the laboratory separately, and when they get to the laboratory, they do not dehydrate them. They simply collect the sap and extract. They've perfected a process to extract that sap very repeatably. So it's very repeatable from one sample to the next. And they extract that sap and they analyze the nutrient content of that sap rather than the total dry matter. So this is going to give you very different numbers from what you're used to seeing. It's not going to be 2.5% calcium on a dry matter basis. We're not talking about calcium in the neighborhood of 2,000 to 3,000 parts per million. It's a completely different number, takes some getting used to, but we find that the sap analysis is much more accurate, it's much more sensitive. The needle moves much more quickly when something is going on in the crop. It correlates with what is happening in the field much more accurately, and perhaps most valuable of all for us as farm managers and consultants is that it picks up nutrient deficiencies 3 to 4 weeks earlier than a regular tissue analysis will. Because if you have, let's say you have a crop that is running deficient on calcium. There's not enough calcium moving from the root system through the xylem up to the upper parts of the plant. With the plant has had adequate levels of calcium up to this point, and one day the calcium needle drops, the availability drops by 60%. There's still some calcium there, but there's no longer enough. When you do a tissue analysis, that tissue analysis will report all the calcium that has accumulated for the last 4 weeks in that leaf, and it will still show that you have adequate levels of calcium. Whereas a sap analysis, when you measure just the sap itself, that calcium number drops very quickly. You can see what is happening well before you can see what is happening with a tissue analysis. So it's a very powerful tool because it now gives you plenty of time to manage it and to do something about it that you would never have had the time window opportunity to manage with tissue analysis. So it's very important. You had a question?
Yes, I was wondering if you found any correlation or efficacy in the cation relationships, the base saturation of the Albrecht and Kinsey concept.
So the question was, have we observed any correlation between soil mineral balance, cation exchange capacity, mineral balance using the Albrecht model and sap analysis? Is that your question? The short answer is no. There is no correlation between the mineral profile that is in the soil and the mineral profile that is absorbed by plants. And this, we talk a lot about the importance of biology. And what I can tell you very clearly and very simply that sap analysis has revealed very clearly is that biology trumps chemistry. You can have the perfectly balanced soil from a chemistry perspective and still grow a really unhealthy crop that does not have a good nutrient balance. And you can have soil that has a very poorly balanced chemistry profile but has really aggressive biology, and the crop does extremely well. So biology trumps chemistry every single time. Whenever we have really aggressive biology, it can overcome a lot of chemistry imbalances. So we see that very, very clearly. Yes?
One of the Achilles heels to tissue analysis has always been drought stress or excess water. The plant will either not pull it in or for whatever reason. How does the sap compare, do you feel like, with environmental conditions? Is there a best time or the best time to stay away? Or?
So that's a really good question. And it's a question that we started exploring this last year to try to understand better. And there are very noticeable and pronounced differences in the concentrations of nutrients in plant sap in different species. So if you compare cherry leaves with a cucumber leaf, for example, there's this pronounced difference in the water concentration in those leaves and in the amount of water in those leaves. So as a general rule, the cucumber leaves would tend to have a lower nutrient concentration in the sap compared to the cherry leaves. But yet there isn't enough of a differential to describe the differences in water concentrations. In fact, if you look at those two, the phosphorus, desired levels of phosphorus on cherry leaves versus cucumber leaves, and the sap concentration is almost identical, as well as with a number of other nutrients. And other nutrients, it varies. The short answer is that it is a concern that we have. It's something that we've tried to analyze, and to the best of our knowledge today, we have not been able to detect any differences between very dry conditions and very wet conditions. That doesn't really quite make sense for us yet. I don't fully understand it, but at this point, we don't see any substantial differences.
How about a diurnal? Have you looked at that? Study times of the day?
Yes, we have. We expected to see some differences, and we do see some slight differences, but they're very, very slight. It's not like a petiole analysis. Petiole analysis, you see these wild fluctuations. We didn't see that when we were actually measuring the leaf itself. Yep.
So based on your earlier conversation, if the tree is moving all its nutrients at night,
Yep.
when should we take the leaf sample, and how many times per year based on this 3 to 4 weeks of looking ahead?
So the ideal time for sap analysis is early in the morning at dawn. That's when you have the least amount of nutrient movement. And so that's when we recommend taking leaf samples. It's also the cooler part of the day. You don't have photosynthesis or transpiration already starting to happen, in most environments at least. And so that is the ideal time that we prefer to take sap analysis. We use sap analysis as a very strong proactive management tool both during the growing season and year over year. And so to accomplish that, it varies a little bit. Most crops, we recommend farmers take samples every 2 weeks throughout the entire growing season. And for some crops like lettuce, that is a 6 to an 8 week turnover, we do it every week. And once you start doing that on a few crops, you won't be able to imagine how you ever made it without that tool. It's an incredibly powerful tool because what you'll observe is, and it's not only an in-season tool where you can make adjustments in season, but it's also a tool that works that you can use for proactive management year over year. So what you'll notice is that maybe you have a tomato crop and you notice that you have generous levels of potassium all the way up until a certain stage in the growing season, and your potassium levels just drop off dramatically. And now you can change how you manage potassium and dry potassium applications the following year to address that specific problem. And you can see that, you can see nutrient trends and nutrient moves. And in fact, one of the tools that we use is a graphing tool to graph out all these nutrient movement in the new leaf versus the old leaf throughout the entire growing season. It's a really fascinating tool to be able to see how nutrients are trending.
Is there any correlation, or have you ever laid over any weather patterns on this kind of information too?
There is some correlation between weather and specific nutrients, like nitrogen, for example. If you have extreme amounts of moisture or water, then it can definitely deplete nitrogen availability and other soluble nutrients. But for the most part, there is very little correlation between. There's not a lot of direct correlation. Most of it is indirect.
What about correlation in what's happening between different kinds of groups of plants? For example, I mean, are all apple varieties kind of similar? All tree fruit? Can you break it into tree fruits, forages, vegetables, something like that?
On smaller operations, we tend to pick one indicator species, and we just do, or an indicator field. If we're working with 10,000 acre corn and soybean operation, there's no way we're going to analyze everything on that entire farm. So we identify by soil type or by specific variety, and we select an indicator species and manage the rest of the operation to those indicator species. Now, if you're growing high value fruit and vegetable crops, there are some crops that tend to be similar, but there are also some crops that are distinctly different. There are substantial differences in a variety to variety basis on strawberries, on cherries, on apples. If you have large enough acreage, large enough blocks that you can do on a variety by variety basis, it will be incredibly valuable because you're able to fine tune specifically by variety. When we're with the strawberry growers in California, the cherry growers in Oregon that we're working with, we're actually now dialing in nutrition specific to each variety, and we're observing that specific varieties have very different nutritional requirements. And you're able to, once you start fine-tuning that, you're able to go to a next level and a next much higher level of performance and fruit quality.
Do we also have to add in rootstock as well?
Rootstock does make a slight difference, but not nearly as much as the variety itself.
Okay.
Yep. All right, so great questions. Thank you for the discussion. So if we look at these nutrient interactions, there's also some very interesting interactions that happen diagonally across the chart, where we know that phosphorus has interesting relationships with iron, manganese, and zinc. Zinc in particular. Again, we have calcium, boron, silicon. One of the things that... so this next piece is where it starts getting really interesting. These four highlighted nutrient elements, nitrogen, phosphorus, potassium, and magnesium, are four elements that are considered highly mobile. They move around wherever the plant needs them very, very quickly. In 24 hours, in one 24-hour photo period, they can move from old leaves to new leaves or from old leaves into fruit. So again, if you remember, one of the pieces that I pointed out is that the optimal nutrient points, plants will do everything they can to keep nutrition at optimal levels in the new growth and the new shoots, or in the fruit at different stages of development. So if the soil is unable to supply the plant's requirements for one of these four elements, it will quickly begin pulling them out of the lower older leaves and moving it up to the new growth and up into the fruit. So that means that for these four elements, deficiencies will always show up on the low leaves first, which is a very strong contraindication for the historical use of tissue analysis where we only measured new growth. Because deficiencies of these 4 elements always show up on the bottom leaves first because they're being moved from the bottom leaves upward. The same also holds true for these elements, sodium, sulfur, and chloride. These are considered mobile. They're not as highly mobile. It takes them 72 to 96 hours to move around. They don't move quite as rapidly, but they do also move around fairly readily in plant structure. So what that means is that all of these major macronutrients across the top half of the chart, with the exception of calcium, can move around. They can move around in plant structure. This is really valuable when we look at a sap analysis, when we look at the new leaves versus the old leaves. So when plants have a deficiency of these mobile elements, the deficiency shows up on the old leaves first. When they have a surplus, when they have an excess, that surplus is going to show up on the old leaves first. Again, because they want to do everything they can to keep the new growth at optimal balance points. So let's take magnesium as an example. Magnesium is one of the major 4 that is considered highly mobile. If we have an apple tree that has a slight magnesium deficiency, it might have 400 parts per million of magnesium at the top and 250 parts per million in the old. That is a signal that that plant has started pulling magnesium out of the bottom and moving it up to the top. Or vice versa. Let's say, again, this particular variety is signaling us that it wants 400, so it's keeping 400 at the top, but now you have 1,000 in the bottom. Now it's signaling, I have a surplus of magnesium. I have way more magnesium than I need, and it's going to store that surplus of magnesium in the lower, older leaves. As I mentioned briefly earlier, this is the foundational reason for almost all of the diseases that infect the old leaves first. So the classical example is early blight. Early blight is supposedly caused by a fungal organism called Alternaria, I forget the variety, the species name, but an Alternaria subspecies, and Alternaria solani. And Alternaria solani is in fact not a pathogenic fungi. So I'm going to give you a slight diversion here because I think this is something very important. So just a very brief overview, there are 4 different groups of fungi in general. There's one group called the mycorrhizae. They colonize living root systems. Many of you may have heard of mycorrhizal fungi. There's a second group called the endophytes. You've probably heard of endophyte-free fescue. Endophytes actually live inside plant structure. There's a third group called the epiphytes. Epiphytes live on the leaf surface. And then there's a fourth group called saprophytes. The saprophytes are decomposers that decompose non-living plant residue. So the interesting part, the fascinating part about this discussion is that all of these organisms, the saprophytes, all of the soil-borne pathogens, what we refer to as soil-borne pathogens, are all saprophytes. So verticillium, pythium, phytophthora, fusarium, rhizoctonia are all saprophytes. So let's say, for example, if you have a garden and you put hay or straw or leaf mulch on that garden and it gets rained on several times, you come back 4 to 6 weeks later and you pull it apart, you see this white mycelium growing all through that. Have you guys seen that? Guess what that is? That's verticillium. That's verticillium in its natural function as a decomposer, as a saprophyte. As in a second example of this, fusarium is also in this group. So when you have a field of a vegetable crop, let's say you have a field of watermelons that has a severe fusarium infection and you have a second field that does not have any fusarium, the fusarium population in that soil is identical. There is no difference in the fusarium population between an infected field and an uninfected field. The only difference is you have a plant that is very susceptible and that allows that fusarium to express itself. Now, let's come back to early blight. The interesting part is that there are some of these fungi that cross over. They are members of more than one group. And the Alternaria family is one of these. Alternaria are both saprophytes, they are decomposers, and they're also epiphytes. They live on the leaf surface and they colonize the leaf surface. So for this family, the entire solanaceous family, peppers, eggplants, potatoes, tomatoes, have alternaria on the leaf surface, and they have a symbiotic relationship with alternaria, much in the same way that we have microbes in the soil that have a symbiotic relationship with plants, where the plants are both providing the alternaria with leaf exudates, carbohydrates and amino acids and so forth, and the alternaria is in exchange digesting dust and residue that lands on the leaf surface, making it available to the leaf, and also is protecting, the alternaria in particular is one of the organisms that is effective in preventing these plants from mildew attacks. This is one of the reasons why this family, the solanaceous family, does not have frequent infections of downy and powdery mildew, even though it can be right next to a cucumber crop that has severe infections of downy or powdery mildew. It's because it has alternaria on the leaf surface. So now, we have a tomato crop that is about 20 inches to 2 feet tall. The first set of fruit is about 2 inches in diameter. The second set is about 1 inch in diameter. And they have a lot of blossoming and pollination happening. You've just started, that plant has started filling fruit, and now all of a sudden has a tremendous potassium draw. If the soil is unable to supply that plant's potassium requirements, it will pull the potassium in particular, but in reality, all of the soluble electrolytes. So potassium, nitrogen, magnesium, everything that is soluble in plant sap, it will pull all of that out of the lower older leaves, move it up to into the fruit, into the upper part of the plant, and it shuts off all communication with that leaf. Now, this is really interesting. When you pull out all the electrolytes out of that leaf, what that means is that that leaf now becomes electrically dead. See, we tend to think of life and living processes in terms of chemistry and biochemistry, but the reality is that all living processes are fundamentally electrical. Even if you're Amish, you're electrical. So what happens is they pull out all the electrolytes from these leaves. Now that leaf becomes electrically dead. Now you have this alternaria on the leaf surface that has had a symbiotic relationship with that plant, with that leaf up to this point. Now the leaf is no longer photosynthesizing, it's no longer feeding the alternaria. Now the alternaria it's also a saprophyte, remember, it's also a decomposer. It perceives this leaf to be electrically dead, it begins feeding on the leaf, and 5 to 7 days later, you see the first visual expression of that as these small specks that we call the beginnings of early blight. The reality is early blight is nothing other than a pure potassium deficiency. It can be completely prevented and managed by supplying adequate levels of potassium. And as an indicator of this, think about how early blight moves within a plant. It will infect a leaf, it'll consume that entire leaf right back to the main stem, and boom, there it stops. Early blight does not infect the main stem because that plant has cut off communication with that leaf after it pulled out all the soluble electrolytes. Early blight never impacts the main stem. So early blight is one of the classical examples of nutrient deficiencies in being in lower older leaves and then translating into a specific disease. Yes?
So in the early to mid-60s, early blight as a disease of tomatoes showed up in the Chicago area, relative to mine. After a lifetime of growing tomatoes, and it never showed up before. A few years later, it showed up in this area. Same thing, never saw it in generations. All of a sudden, it's there. So how did that happen?
How much are you going to pay me to answer that question? It happened because of, excuse me, because of a genetic shift and a genetic change in a specific species in the Alternaria family. So what was it that triggered that change? What was it that triggered that shift? There's discussions that you can have about pathogenicity of these various pathogens at length, but the reality is that almost all of the organisms, whether you're talking about Erwinia or Xanthomonas or Pseudomonas or almost all these organisms that you want to talk about, that we perceive to be diseases and have major problems managing with as diseases today, have dozens of counterparts in the exact same family that are beneficials. And so the question is, what triggered this specific organism to become a pathogen? What was the environmental trigger, or what was the trigger that caused that switch? And those triggers can be nutritional. They can be, well, it can be a number of different factors. It's a conversation I prefer to have offline. But yeah, was that an answer to your question?
Yes, thank you.
All right, so are there any other questions on nutrient mobility and nutrient movement, nutrient transport? One piece that I failed to mention is that, so you have all of these cation, or all these macronutrients, all the major elements move around. They're fairly mobile. They move around relatively quickly. If you look at all the trace minerals for the most part are relatively immobile. Some of them move around a little bit. Some of them move around more than others, but for the most part, they don't move around very readily. There are two in particular that are considered to be completely immobile, and those two are manganese and boron. I talked about the fact that manganese does not transport in the phloem tissue. Supposedly, manganese is capable, boron is capable of being transported in the phloem tissue, but it tends to often associate with calcium, which is not. And as a result, boron is also usually very readily moved in phloem transport.